Let's continue. Let me open the table of content first. Okay, we are still in chapter 27 here, interlude thread API, and still in homework code here. Let me open that. This one, we are still in homework code. Now let's take a look at question 5. Now run Helgrind on main deadlock global.c. Examine the code. Does it have the same problem that main deadlock.c has? Should Helgrind be reporting the same error? What does this tell you about tools like Helgrind? Okay, let me open my terminal emulator here. Okay, what is it again? Main deadlock.c. I think this one. If I remember correctly, the problem is incorrect order of the log for both thread here. Can let me recompile that, I guess. Threads API, and then what is it called? Makefile. Okay, main deadlock here. Okay, main. Alright, up to that. Right. Okay, now let me run that using Helgrind tool Helgrind thread API deadlock. Right, this one. Log order violated. Okay. And now let's take a look at the main deadlock global. This one. Okay. Okay. Oh. There's even a global here. Alright. Probably Helgrind will report the same thing, right? Because the order did not match here. Right, this one M2 M1, this one M1 M2. Probably, but I'm not sure. Okay. I guess global. Yeah, global. This one. Okay. Right, global. Okay. Log order violate. Okay. Yeah, I assume this is the same, maybe. As the, what is it called? As the non-global one. And now let's try changing the order, right? Make the log order similar. Thing like this. M2, M1. Recompile that. Okay, 0 error. So it is the same problem, I assume. But that is quite interesting. When did we... Oh, okay. We log the global one before entering this condition. Okay. Alright. Okay, should Hell client be reporting the same error? Probably, because from what I can see, the problem is the same, the order of the log for the thread. What does this tell you about tools like Hellcrine? The tool that is useful to check if there is any problem with the thread, I guess, either thread creation or thread log, maybe something like that. Let's next look at main signal.c. Oh, that also make me wonder, is there any significant effect if we have, what is it called? If we have different order of log here. What is it called? What is the effect if we have different log order for each thread? Yeah, I'm not sure. Maybe let's put that in the, what is it called? In the question here. Chapter 27. Okay, 27. What happened when we have mismatch log order? Mismatch log order for the thread, for each thread, maybe something like that. Wait a minute. That make me curious. If I change this, right, is there gonna be any effect? Like we unlock M2 first and then M2, M1 I mean. Okay. global, I mean file grind tool, file grind, nothing. So the important one is this log, I assume, rather than the unlock sequence, maybe something like that. Yeah, still 0 error. Okay. Right, log order violated. Okay. Let's next look at main designal. This code use a variable done to signal that the child is done and that the parent can now continue. Why is this code inefficient? What does the parent end up spending its time doing? Particularly if the child thread takes a long time to complete. Let me check. Signal. Oh. Okay. Well, okay. Why is this code inefficient? Because the parent is not idle, I guess. The parent keep doing the iteration until done not equal to 0, which means the parent also take up CPU resource, something like that. Maybe that's why this code is inefficient. And well, if I remember correctly, rather than using this kind of looping or iteration, see, don't ever do this for the following reason. First, it performs poorly in many cases. Spinning for a long time just wastes CPU cycles. Second, it is error prone, right? As recent research show, it is surprisingly easy to make mistake when using flag as above to synchronize between threads. In that study, roughly half the use of this ad hoc synchronization were buggy. Don't be lazy, use condition variable even when you think you can get away without doing so, right? So maybe the inefficient part is this one with CPU cycles, because it's still processing the iteration over and over again. Instead, we should use the condition variable here. I'm still not sure about the condition variable, because we will talk about that on the next chapter, chapter 30, right? This is just, what is it called? To make us aware that condition variable exists, something like that. If one thread is waiting for another to do something before it can continue, two primary routines are used by program wishing to interact in this way. Yeah, we can use this one. To use a condition variable, one has to in addition have a log that is associated with this condition. When calling either of the above routine, this log should be held. Okay, this routine or function put the calling thread to sleep and thus wait for some other thread to signal it. Usually when something in the program has changed that the now sleeping thread may care about, typical usage looks like this. Okay, right. Log, ready, wait, condition, okay, and then unlock. Okay. In this code, after initialization of the relevant log and condition, yeah, let me review this for a bit. Okay, a thread checks to see if the variable ready has yet been set to something other than 0. Yeah, this footnote is just another way to initialize the condition using this one, put that condition in it, and don't forget to use condition test try to after the initialization. This is the dynamic way to initialize the condition instead of using this one. Sounds like more work, it is. So there is that. The code to wake a thread which would run in some other thread looks like this. Okay, change ready, and then condition signal, okay, and then unlock. A few things to note about this code sequence. First, when you signaling as well as when modifying the global variable ready, we always make sure to have the log held. This ensures that we don't accidentally introduce a race condition into our code. Okay. Second, you might notice that the wait call takes a log as its second parameter, whereas the signal call only takes a condition. The reason for this difference is that the wait call, in addition to putting the calling thread to sleep, release the log when putting set caller to sleep. The wait call, in addition to putting the calling thread to sleep, release the log when putting set caller to sleep. Release the log when putting set caller to sleep. Imagine if it did not. How could the other thread acquire that log and signal it to wake up? Right. We will have the double log if we didn't release the log from here, I guess. Now that make me wonder, why do we need to unlock again? Maybe when what is it called? The condition wait here already finished, which means the thread wake up again, the log we acquire the lock again, and then we need to unlock that. Maybe something like that. So what is it? Pthread conwait release the lock when putting the thread to sleep. Acquire. Wait. Okay. Acquire the lock when waking the thread up. Maybe something like this. Yeah, maybe. So when we are putting the thread to sleep, wait, and then when waking up, we acquire again. So that's why we need to unlock the lock here. Maybe. The wait call. In addition to putting the call thread to sleep, release the lock when putting set caller to sleep. Imagine if it did not. How could the other thread acquire the lock and signal it to wake up? However, before returning after being woken, right, the pthread conwait reacquires, right, reacquires the lock, thus ensuring that any time the waiting thread is running between the lock acquired at the beginning of the wait sequence and the lock release at the end, it holds the lock, right? We are making sure that we have the lock again before waking the thread, I guess, and then after that we unlock the lock here. We release the lock. Okay. One last oddity. The waiting thread rejects the condition in a while loop instead of a simple if statement. We will discuss this issue in detail when we study condition variable in future chapter. It is chapter 30 here. Condition variable. Okay. But in general, a while loop is the simple and safe thing to do, although it rejects the condition, perhaps adding a little overhead. There are some pthread implementations that could spuriously wake up a waiting thread in such a case without rejecting. The waiting thread will continue thinking that the condition has changed, even though it has not. It is effortless to view waking up as a hint that something might have changed rather than an absolute fact. Note that sometimes it is tempting to use a simple flag, okay, to signal between two threads instead of a condition variable and associate log. See, we can do this, right? Similar to this. What is it called? This condition, maybe something like that. This code that we take a look for the question 6 here. Main test signal, right? Why is this code inefficient? Because of this one, which means that both thread is active rather than putting the parent thread to sleep, which means that we take up some CPU resource. while doing this. That's why this code is inefficient, I assume. At least according to this one. It performs poorly in many cases. Spinning for a long time just wastes CPU cycle, right? It is still executing this over and over again. Okay, and then now run Valgrind on this program. What does it report? Is the code correct? Let me try compiling that main signal. Okay, this one main signal. Okay. Oh, okay. Possible data restoring read of size 4. Oh, this conflict with a previous byte of size 4 byte thread. Okay, data is when reading. I assume when reading this global variable, maybe. Okay. I mean, well, we execute this. At the same time, another thread might already putting this to 1. So what we read in this one is not the up-to-date value that the worker function here changed. Maybe that's why it is the possible data is during read. Okay, is the code correct? Probably not. What does it report? It reports the possible data race during read of the global variable done. Code correct or not? Probably not. Okay, now look at a slightly modified version of the code which is found in main signal CV. Oh, CV in here stands for condition variable. Okay, this version uses a condition variable to do the signaling and associate log. Why is this code prefer to the previous version? Is it correctness or performance or both? Let me check. This one, guess. Oh, there is a lot going on here. Let me compare that. This is without the condition variable, right? The CV condition variable, and this is with condition variable. Okay, simple synchronizer allow one thread to wait for another structure. Synchronizer underscore T has all the needed data methods are this one, I guess. Init called by one thread, wait to wait for a thread, done to indicate thread is done. Okay, we have global variable here as signal init. Okay, signal init, signal done, mutek init, condition init. Okay, then become 0. Okay, I mean, if we declare the global variable here, I assume we already have default value, maybe something like that, but it doesn't matter if we want to initialize the value again. Signal done. Okay, tag log, change to 1, condition signal unlock. Okay, we are signaling that the thread can wake up, I guess. Then signal wait, right? The clock waiting for the signal or the condition, I guess, to change. And then we unlock again. This should print first. Okay, signal done. Oh, okay, signal wait in this one. Signal init, signal wait. But why there is no destroy? Right. Like signal clean up or something like that, you know. Can according to this one, the footnote, one can use pthread con init and pthread con destroy instead of the static initializer. Pthread con initializer sounds like more work. It is. So if we use this, I assume we expect to also destroy that. Maybe. Now wait. Okay. Wait a minute. Let me check. Note that a corresponding call to pthread should also be made when you're done with the log. Okay, let me check. Pthread mutex destroy. Okay, something like this. Is there an example? Okay. Only this one is unlocking immediately destroy the mutex. Maybe not. Destroy a mutex object freeing the resource it might hold. The mutex must be unlocked on entrance. Okay. No resources are associated with mutex object, thus pthread mutex destroy actually does nothing except checking that the mutex is unlocked. Oh, okay. In the Linux thread implementation, no resources are associated with mutex object. Thus pthread mutex destroy actually does nothing except checking the mutex is unlocked. Okay, this is specific to Linux implementation, I assume. So maybe it's fine because no resource is, what is it called? No resource associated with the mutex object here, on Linux at least. Let me compile that. Make signal CV. Okay. This should print first. This should print last. Okay. 0 errors. Alright. Okay. Main signal test CV. Version use a condition variable to do the signaling and associate log. Why is this code prefer to the previous version? Because the previous version might have data race condition here, while the main thread reading this global variable, another thread might change the value of this global variable. So it becomes race condition whether the other thread read first or the main thread read first, So that is the first drawback, I guess. And then the second drawback is that the main thread is still active rather than putting that to sleep, which means the main thread take the CPU resource or something like that to execute this iteration, which might be inefficient. Maybe those two possible data race during reading of done variable, and then what is it called again? The main thread is still active rather than sleep, and that take some system resource, something like that. That is the drawback in this implementation without the condition variable. Now, is it correctness or performance or both? I am still not sure if this is correct or not, but for performance, maybe, at least what I understand, that the main thread is putting to sleep because of this conwait here. So instead of wasting system resource, we are putting the thread to sleep and then wake up again after another thread finish here, right? So maybe there is that. Once again, run Helgrind on main signal CV. Does it report any error? Nope. It reports 0 error on the main signal CV here. this make me curious. Can I do this? Signal clean up. Or maybe, yeah, let's call it signal clean up. Synchronizer T, right? V-thread. Is there any destroy? No. Okay. Only init. Yeah, only init, no destroy. Let me check. Vthread mutex destroy. Return value. Okay, this is interesting. Mutex init always return 0. Oh. Okay, so how did we know if there is any problem with mutex init? Like multiple initialization or something like that? Initialize the mutex object point to mutex. Okay. Support only one mutex attributes. Okay. Yeah, I'm not sure yet. The other mutex function return 0 on success and a non-zero error code on error. Okay. Well, destroy. Okay. Let's do this manually. Tag is currently low. Okay. Yeah, I just want to try this out. How to properly clean up. Okay. Oh. Well, I guess. Don't forget this one. And also, not only mutex but condition 2. Can we initialize dynamically here? Right. Okay. Okay, and then after wait, I suppose we can do this. Okay, at least it compiled. Let me check. Okay, still 0 errors at least. And let me run this. Okay, this should print first, this should print last. Okay, in case anyone wants to try to clean up, I guess. Now let's try putting the clean up first before wait. I assume that's gonna cause any problem. Let me check. Tool. Yeah, that's gonna cause some problem. Cordam, right? Okay. So be careful of that. Right, assertion. This one. Bitrate mutex logs not equal 0, which means that the what is it called? That the mutex still what is it called? Still locked, not unlocked. See, in the Linux it is only checking mutex is unlocked or not. The mutex is currently locked. With that mutex destroy function returns the following error code on error. It is the mutex is currently locked. So make sure that we unlock first before we destroy the mutex. Something like that. Okay. Hello advocate. What are you studying? I'm studying operating system here. Reading this book. Operating system 3 easy piece. Let me copy this to the chat, or you can take a look at the description. There are some resources there. Okay, and now I am on chapter 27, taking a look at the thread API here for concurrency here. Okay, I guess we finish the homework section here on chapter 27. I mean, this is just a reference for the thread API. We haven't talked about the concept yet. For example, like log here. We will learn about that on chapter 28, the next chapter. And then there is also condition variable. We will be talking about that on chapter 30. So this is like maybe the introduction to the thread API before we learn about the concept in the future chapter. Okay, so I guess let's continue this chapter 28 on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.